say less than? Yeah, I guess here I want to say less than actually, yeah. Because this is strictly, this expression is strictly larger than this one. I've added this side's bigger by p plus 1. So in fact, p squared plus m is between p squared and p plus 1 squared. Okay, and this is kind of what I was rambling about earlier with the 1 billion sort of thing, right? If you pump this once, what you end up with is a string whose length is like lost in space in between the previous perfect square and like the next perfect square. By necessity, it will be. And so therefore, okay, even more sort of, basic fact about numbers, which I will not justify, that, there are no perfect squares in between a perfect square and the next perfect square. And this shows that p squared plus m is not a perfect square. Okay, this is the best I can do, I think, on this. Okay, so sort of, and by above, well, since p squared plus m is not a perfect square, this is kind of hard, is not a perfect square, then that means that this string x y squared z is in fact not in D by definition of D. So on the one hand, the pumping lemma is telling me that when you pump the string r once, you get another string that must be in the language. But on the other hand, by looking at this string and analyzing it, it's just not in the language. And so we have a contradiction, and thus we conclude that, we conclude, what did I do? Did I call this 10 or something on the previous, I don't remember, who cares about the numbers. But I conclude, so D is not regular. Okay, that was slow, but I think thorough. One more, and this is not, I think these are sufficiently different from each other that they are not a waste of time. In other words, more learning continues to happen as you do more of these up to a point. The first one was very similar to the one we did on the video, so maybe that one was nothing new, but of course you were being forced to do it yourself. And then this one was quite new, I think, because, well, I think it was. And then this one I'm about to do is also sort of new. I've had people in the past definitely get stuck here on this one, number E. This time I am going to be crafty and do something like what I was saying. Okay, and then the last one is sort of just another repeat. So okay, let's go. I have a new language to consider. What's this new language? It's called E. So take E to be the set of all strings of the form A to the I, B to the J, such that I is greater than J. Okay. Well. This, I claim, is not regular. Why is it not regular? Well, once again, I now it's seemingly this should you might think be kind of an easier task or something like that for a machine to take account of, for a finite state machine to handle, easier than that there are the same number of A's and B's, because we just have to make sure that there are more A's than B's, but it really is the same problem, because to assure that there are more A's than B's, we have to keep a track of the number of A's which have occurred up to the point when the B's start. And once the B's start, we need to make sure that there are fewer B's than there were A's. So we still need some kind of way of storing how many A's there were, and there's just no way to do that with a finite state machine. So I feel like this language is, once again, intuitively not regular, and that I think that intuition and thinking about machines is important to be able to do the proof, because you still have to come up, with your counterexample string. Okay, so I introduced a language. I suppose that this language is regular. I applied the pumping lemma to this language, and the pumping lemma says that there exists a p such that for any string in this language, which is long enough, longer than the pumping length, then it can be split up into these three pieces, x, y, and z, such that there's some substring of some significant, substantial length, non-zero length, is being processed during that loop. That the whole lead up to the loop and the loop happen before we get to the pumping length, and that also that this machine can be pumped. I feel like that picture was actually kind of nice, but I'm not going to draw it again. For any I might draw it again. Greater than or equal to 0. The picture was that there was a start state, that some stuff happened, then you hit before p states are exhausted. We must have hit some state twice, because they're only p states, but the string is longer than p, so somewhere on those first p states, which is to say, somewhere in the first p plus p characters of your string, a loop happens. And then there's the final bit, leading to an accept state. And so once again, the intuition here is that this is x, this is y, and this is z, and we're going, the arrows go this way, of course, cha-cha, cha-cha. Okay, but that was all this is all sort of buried under the hood when it comes to invoking the pumping lemma, because it just doesn't even refer to machines at all. The pumping lemma, it just refers to this mysterious pumping length. Okay, enough commentary. Let's keep going. La 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 la. Good. So now it is time to come up with a string which captures the fundamental irregularity of this language. And I guess it's some kind of like evil game, right? You have a machine, it has p states, and then you're just standing there and you're just gonna trick that freaking machine, and you're going to just. It's like the old cartoon where you stand, there's the screaming dog on a leash, and then the rooster stands 2 feet longer than the leash of the dog, and you just watch the dog just fail. Here we're just going to watch this string fail, and we're going to watch, or rather we're going to watch this machine, a machine that we're not even explicitly invoking. We're going to watch this machine sort of fail to correctly accept a string, because we're just going to make that string so damn long that it can't be processed given the finite number of states that our machine has. And our machine effectively has p states. And if our machine has p states, then how do we trick this machine? We give it a string which has so many a's in it that this machine just can't remember how many a's there were. This is the idea. And so what we're now going to do is we're going to consider the string r, where r is a to the p plus 1, b to the p. So, in other words, I make my string have more a's than the number of states in the machine that's supposedly built to recognize this string. And so the machine's just going to run out of memory before it can keep track of the number of a's there are. And just for purposes of specificity, I will let there be p b's. And okay, this is a string. Well, what's the order again? That's 4, so 5. I just state that this string r is a member of my language. This should say E. R is a member of my language E, by definition of E. It has it consists of a string of A's followed by a string of B's with more A's than B's. Okay? Next, I show that it meets the other condition of the pumping lemma, which is that it's long enough. It is. The length of R is in fact 2p plus 1, which is certainly greater than or equal to p. So the pumping lemma applies. Now I invoke the pumping lemma explicitly. So, by the pumping lemma, as applied to this language, as applied to this string can be pumped. R can be pumped. R can be, no, not pumped. R can be expressed in the form x, y, z, where x, y, and z meet the conditions above. Meet the conditions above. All right. And now what? Okay. What's the issue? Oh, should we perform an analysis? I guess we should, right? What's the analysis on this string? Well, here we use the fact that how do I write this again? Oh yeah. So since the total length of the x part and the y part has to be less than or equal to p, but the first but I guess I should write this out. But the first p plus one characters of R are all A's, then in fact I can tell you that x and y consist entirely of A's. Then x and y consist entirely of A's. In other words, I made my string so long that the lead up to the loop and the loopy part, which must exist, all happens while we're still processing the A part of this string R. Okay, and so for purposes of specificity, let's and then since y has to be greater than 0, let's just let the length of y be m. In other words, I am now telling you that y is of length m, which is to say that m characters are processed during this loop, and that those are all A's. Okay, well, now I start to see what is going on. Because, hope I'm doing this right. Yeah, I am. Because, and here we're going to do something called pumping down. And this is something that hasn't come up yet, so some people have found this to be hard. Pumping down says, note that because this string must have this form, lead up to the loop, finish, then if that's the structure of my string R, then simply not doing the loop at all should also lead to an except state. In other words, if x, y, z is a string of this language, then so must x, z be a string of this language. Previously we've been pumping up, now we're going to pump down. And that's why, built into the theorem, is that, x, y sub I, z should be a string of this language for any I greater than or equal to 0. In other words, you can pump down, which I think is very intuitively clear from the picture, right? You should be able to skip the y substring entirely and still make it to the except state. Okay, so now we invoke, losing track of my, no, I think we're still good. Now we get to step 9, and in step 9 we say, okay, by the pumping lemma, I now introduce a new string. That string is just xz. xz must be a member of my language E. Okay, but, and I guess this is step 10 or something, but that is a problem, because what is this string xz? Well, xz consists of, well, it's just string, where is it? It's the string a to the p plus 1 b to the p, but I've taken out y. And what was y? Y consisted entirely of m a's. So if y consists entirely of m a's, and I subtract those m a's out, then the string xz must in fact be a to the p plus 1 minus m b to the p. So I have subtracted, I have sort of cut or deleted or something precisely A characters when I avoided this loop. Okay, but now I have an argument, which is that this string is no longer in the language. Because, let's see, what's the smoothest way to do this? If, well, since geez, what do I know? That m is greater than or equal to 1 or something like that? Or m is greater than 0? Maybe I want to say it like that. Okay, so m is greater than 0. That's a fact. Because the length of y is to be greater than or equal to 0. And if m is greater than 0, then now I sort of add p to both sides. So p, this is so dumb. So p is, perhaps I should look at my notes. P is less than, no, I think I want that m is greater than or equal to 1. Yeah, that's the smoother way to do it. M is greater than 0, so m is greater than or equal to 1. That's true because m is an integer, of course. And if m is greater than or equal to 1, then m plus p is greater than or equal to p plus 1. So I just added p to both sides of this. No one goes into this level of detail. But now if you subtract m from both sides here, then this p plus 1 minus m thing has to be less than or equal to p. Okay, so this argument is now being, it's not even an argument, it's just a little bit of very simple algebra, is being invoked to show that I now claim that this new string in which I pumped down by m, the casual way of putting it is that this string just barely met the requirements of E, because it had, to be an E you have to have more A's than B's, but this string had just one more A than B's. But now I just took out m A's, so since m is at least 1, there are now fewer A's than B's, or perhaps equal if m is 1, but that's still good enough to make it fail the condition for being an E. So anyway, the algebra speaks for itself, that we now see that that if xz is of this form, so xz has fewer, has less than or equal to, I think we're just done, right? xz is just not in E by definition of E. It's not in E because, in fact, the number of A's is less than or equal to the number of B's, whereas to be in E, the number of A's has to be greater than the number of B's. And now we have a contradiction, because this string xz is in E, but it's also not in E. Contradiction, and we conclude, so E is not regular. Whew. Okay, that was pretty hard. Time check. Yeah, goodbye.